Welcome to our next topic, exponential functions and logarithms, from chapter 13 of our textbook. Now we are going to be looking at what each of the functions are, how we can solve equations, how we can manipulate equations and expressions and solve inequalities and graph, but also model. So perform modeling with exponential and logarithm functions. Our first module, 13a, looks at the index laws. And with the one learning intention, we hope you understand the rules for manipulating exponential expressions. And by the end of the module, we can use the rules for manipulating exponential expressions. Just some housekeeping before we begin. We're going to be using the term power to represent a term like this. So, which consists of both a base and an exponent / index. So we'll be using these terms exponent and index interchangeably. And when we're talking about the base, we're referencing A, and when we're talking about a power, we're talking about this term in its entirety. Now this brings us to the index laws. We have index laws 1, 2, 3, 4, and 5, and on the next slide we'll look at a few special cases. But let's delve into some of the explanations of what each of them are. So index law 1 says that any two bases multiplied together to a certain exponent, we can equate that by having the same base and then adding the exponents together. So let's just look at an example, x squared times x to the power of 3. This is like saying x times x times x times x times x, which is the same as saying x to the power of 1, 2, 3, 4, 5, or the 2 times 3. Okay. What about index law 2? Saying that a base with a certain exponent divided by the same base with a different exponent can be equated by subtracting each of those exponents. And that works the same way. So if you want to prove each of these, expand out a index term and then test it out. So we're just going to define it here. Index law 3 says that if we have a power which is raised to another exponent, then the result is that these two exponents, the m and the n, are multiplied together. Index law 4 says that the base of a power consisting of two or more multiplied terms raised to a common index can be expressed as each of the terms raised individually to that index. Index law 5 says a base of a power consisting of a fraction can be expressed as the numerator and the denominator raised individually to the same index. So just like with multiplication, division works the same way. We could say that a over b to the power of m is the same as a to the power of m divided by b to the power of m. Let's have a look at two special cases of the index law. The first one, the zero index. So where does this come about? A to the power of 0 equals 1. So anything to the power of 0 equals 1, as long as a is, or that base is not 0. So let's consider just a very basic example, x squared over x squared. This can be rewritten as x times x over x times x. And this very easily is equated to 1. But let's look at this from the lens of, or through the lens of the second index law. Then this can be rewritten as x2 minus 2, or x to the power of 0. So through both of these processes, we've found out that x to the power of 0 equals 1. So once again, assuming that the base is not 0, anything to an exponent of 0 is equal to 1. Similarly, using the second index law, we could see that the subtraction of 2 and 4 results in a base x to the power of negative 2. Whereas if we looked at this same expression, x squared over x to the power of 4, as an expanded form fraction, then what we get is a fraction with a positive index. So what we can say, using that same tact, is that a base with a negative index is the same as the reciprocal of that term with a positive index. Okay, so let's jump into quite a few examples to explore as many different combinations of these index laws as possible. So, 2 to the power of 4 times 2 to the power of 11. Due to the first index law, we could say that this is equal to 2, 4 plus 11, 15. B, x squared times y cubed multiplied by x to the power of 4 and y to the power of 1. Combining our x2 plus 4 and then our y3 plus 1, what we get is x to the power of 6, y to the power of 4. 2x plus x plus 2. So we're essentially adding that second term here. Or the base 2 to the power of 2x plus 2. And lastly, let's look at a special case with something to the power of 0, but we're also going to have to work in some of our index laws in there as well. So 5 squared, 25, 25, anything to the power of 0 is 1. 1 times 5, a to the power of 0, 1 cubed. 1 cubed is 1, so 5 times 1, multiplied by ab squared. We can't simplify anything else there, so let's state our final answer. Okay, using our second index law, we have a couple of divisions. X to the power of 4 minus 2 and y to the power of 3 minus 2. F, 16a to the power of 5 times b, and all of that multiplied by 4, a to the power of 4 b cubed, and then that divided by a to ab, 8ab. So we can simplify this, and this is 2, 2 times 4 is 8, 8, 5 plus 4 is 9, minus 1, 8, b, 1 plus 3 is 4, 4 minus 1, 3. Using our third index law, a power raised to another exponent, we multiply together those the indices. So a power of 3 times 5, 15. Once again, we have that index law. However, we've also got a number in there, 1/2. So we're going to have to equate that to complete our answer. So 3 times 2 is 6. Then 1 to the power of 6 is 1. 2 to the power of 6 is 64. Okay, stepping through here, b to the power of 3 and then that to the power of 2, b to the power of 6, multiplied by b to the power of 2 to the power of 1. So we could say b to the power of negative 2. And then adding these two together using the first index law, b to the power of 4. Okay, all of this to the power of 3, 2 cubed, a to the power of 6, b to the power of 9, times 3 to the power of negative 2, a to the power of negative 2, b to the power of negative 8. So, we could say 2 cubed, 8, a to the power of 6, take away 2, a to the power of 4, b to the power of 9, take away 8, just b, and then all of this over 3 squared, 9. Okay, with this last one, let's expand out these brackets. 2 to the power of 3, a to the power of 9, b to the power of 6, all of this over a to the power of 3, b to the power of 3, c to the power of 6, divided by a to the power of 3, b to the power of negative 3, c to the power of 3. Okay, so we have 8, a to the power of 6, b to the power of 3, and all of this over c to the power of 6. And we're dividing this by a 3, b minus 3, c 3. So using the second index law, we can take away these terms here. 8, a to the power of 6, take away 3, a to the power of 3, b to the power of 3, take away negative 3, b to the power of 6, c to the power of negative 6, take away 3, c to the power of 9. As the denominator. We could also have written 8, a to the power of 3, b to the power of 6, c to the power of negative 9, but we like to write our indices in with positive integers. Okay, so with example 13a.2, simplifying these expressions requires that we actually break down our numbers, bases 12 and 18, and 6 and 12 again, and 9, into their prime factors. So hopefully we can remember our prime decomposition. And let's just step through 12 and 18 together nice and slow. Factors of 12, 3 and 4, and factors of 4, 2 and 2. So 12 can be represented by 3 to the power of 1 times 2 to the power of 2. 18 has factors 2 and 9. And 9 can be broken into 3 and 3. So 18 can be represented by 2 times 3 to the power of 2. Okay, so how does that help us? That means we can rewrite these in part A as 3 times 2 to the power of 2 to the power of n, multiplied by 2 times 3 to the power of 2 to the power of negative 2n. Expanding out each of these brackets, we get 3 to the power of n times 2 to the power of 2n times 2 to the power of negative 2n times 3 to the power of negative 4n. And now that we have two base terms of 3 and two base terms of 2, we can use the first index law to add them together. 3 to the power of n, take away 4n, so 3 to the power of negative 3n, and 2 to the power of 2n, take away 2n, is 1. So 2 to the power of 0, or 1. But we have a negative index here, so let's rewrite this as 1 over 3 to the power of 3n. Okay, so for part B, let's break down 6, 12, and 9 using prime decomposition into their prime factors. So we have 3 to the power of negative 3 times 2 times 3 to the power of 4. 2 to the power of 2 times 3 to the power of negative 3. Okay. And all of this over 3 squared to the power of negative 4 times 2 to the power of negative 2. So we've used this method of prime decomposition so that we can actually combine these terms. We can simplify it further. We have the same basis, therefore we can use the index laws. Okay, so let's look at our terms including base as a base of 3 in the numerator, 3 to the power of negative 3, so negative 3 plus 4, 1, take away 3, negative 2, and then base 2, 2 to the power of 4, and then 2 to the power of 2, take away 3, so negative 6, also negative 2. All of this over 3 to the power of negative 8, and 2 to the power of negative 2. Three to the power of negative 2 minus negative 8, or just 3 to the power of 6. Because our 2's cancelled out. Let's use prime decomposition to break our 6 and 8 down into the prime factors. 3 to the power of 2n times 2 times 3 to the power of n. All of this over 2 cubed to the power of n times 3 to the power of n. Three to the power of 2n plus n times 2 to the power of n. All of this over 2 to the power of 3n times 3 to the power of n. So this and this cancel out, and what we're left with is 3 to the power of 2n over 2 to the power of 2n. So what we can see here is that we have both of these, the numerator and the denominator, are both to the power of both have the same exponent, so we could use the fifth index law to say that this 3 to the power of 2n over 2 to the power of 2n is the same as 3 over 2 to the power of 2n. After practicing, hopefully you can use the rules for manipulating exponential expressions and use each of the 5 index laws. Your suggested questions are at the bottom of your notes, and before you get started, please go on to the mini quiz and test your immediate understanding. Thank you.